Hello, everybody, and welcome to the webinar today. We're going to talk about GLMNET. We have Dr. Trevor Hastie here from Stanford, and he's the GLMNET package maintainer. So I'm going to go ahead and put my slides on full screen mode here and go ahead and introduce the Gotowebinar control panel to everybody. So if you look on your control panel, you'll see an orange button, and this will allow you to maximize and minimize your control panel. And then you can select your audio type. Most people are going to use microphone and speakers mode. If you're in the United States, you can also use telephone mode as well. But microphone and speakers mode is the more popular mode. And go ahead and try to close other applications you might have up that could take bandwidth, things like Skype or Facebook, etc. And then you can also make this webinar full screen as well to see the largest possible screen. And then if you have headphones, it's recommended to use those. You don't really have to use headphones, but it will allow you to hear the voice of myself and Trevor a little more clearly. So let me just introduce myself really quick. I'm Ray DiGiacomo Jr., president of the Orange County R user group, and I'm a master R trainer and a healthcare predictive analytics consultant as well. If you're interested in the Orange County R user group, you can join us on LinkedIn groups, and we're going to be doing a lot of webinars like these in the future. We also do face-to-face events as well. So the webinar we're doing today on GLMNET is being recorded right now, and you'll get an email sometime today within the next few hours with a URL to look at the recording and also the slides as well. These should all be posted up on the internet within the next 7 days, so stay tuned for that. So what I'm going to do now is I'm going to change presenter to Trevor Hastie, Dr. Trevor Hastie of Stanford, and what I'm going to do here is go ahead and find Dr. Trevor Hastie here and make him presenter. So now, Dr. Hastie, you should have presentation controls, and go ahead and show your screen when you're ready.
Can you see my screen?
I can see your screen. It looks great.
Okay, let me just make this.
Yeah, go ahead and get comfortable, and then go ahead and get started whenever you're ready.
Well, hello, everybody. Good morning. Well, at least this morning here in California, it's nice to see we got people from Europe as well. Welcome to the GLMNET webinar. First of all, I'd like to thank Ray DiGiacomo for organizing this and the R user group in Orange County. It's the first webinar for me. Never done this before. It's a little unusual talking to a screen, and my only audience is the dog and the two cats in the room here. But, well, I'm always up for new experiences. So this is a talk about sparse linear models and the GLMNET package. And I've got listed up on the screen here the co-authors. Normally I don't put my own picture up, but since you can't see me, there I am on the left. There's Jerry Friedman, second from the left, who did a lot of the coding of GLMNET, especially the Fortran code. There's Rob Tibshirani, the inventor of the lasso, and a co-author of this package, and graduate student Noah Simon, who wrote and helped develop part of the package, in particular the Cox model part and the multinomial, grouped multinomial part. So let's get started. We're really talking about linear models for wide data, and wide data has become pervasive in data mining and all kinds of problems. Here's some examples. So document classification. By wide data, we mean lots of variables, maybe many more variables than observations. So in document classification, you might have the bag of words model, where you basically score a document for which words are present, say the words in the English dictionary. You can easily have 20,000 words if you just use unigrams, many more if you use bigrams or higher order grams, and you might have 5,000 documents. So many more variables than observations. In genomics, same thing, we might be measuring gene expression, have 40,000 genes and relatively small numbers of subjects, often 100, 200, 500 subjects. Genome-wide association studies, another example, 500,000 SNPs measured along the genome. That was 3 or 4 years ago. These days, 1 million to 2 million SNPs. SNPs are single nucleotide polymorphisms, essentially 3-level factors, and maybe you'll have 2,000 case control subjects. So these are all examples of wide data. And when you've got so many variables, we tend to use linear models. Linear models are rich enough, you know, and are typically too rich. And so we can get away with linear models, and they become very useful again. And so linear regression, logistic regression, Cox models, and so on. So because we got so many variables, you can't, as you probably all know, you cannot just fit a linear model with more variables and observations without some kind of regularization or constraints. So there's several classes of ways of doing this. One class is to just use subsets of the variables. And these days, a very attractive approach is forward stepwise regression, where you build up a model in a forward fashion, add in variables one at a time, and you do this in a greedy fashion until you've reached a point where you're doing a good job and you haven't started overfitting. So I'm a big fan of forward stepwise, and we have very nice, efficient software for doing that. Best subset regression was thought to be the holy grail in the past. Doesn't really work very well for large numbers of variables. The bar keeps on shifting up, but it's essentially a combinatorial explosion to find the best subset of a large set of variables. So the classes of techniques that we're going to focus on today use regularization. And the idea there is you fit the model with all the variables in the model, but you restrict their coefficients in some way. And ridge regression restricts the L2 norm of the coefficients. So in other words, you put a bound on the sum of squares of the coefficients. And what that does, if the bound t is small enough, it shrinks the coefficients towards 0. And that controls the variance. Of course, if you shrink all the way to 0, you'll have a null model. But as you relax t, the coefficients are allowed to grow, and you may be using maximum likelihood or least squares. And ultimately, if the number of variables p is bigger than n, you'll ultimately reach a model that's got 0 error on the training data, and it'll have the minimum norm, L2 norm coefficient. Now, the thing with ridge regression is that although it does control the variance of the coefficients, all the coefficients are in the model. All the variables are in the model. So it doesn't do subset regression. It leave out subsets. So this brings us to the lasso, which was introduced by Rob Tibshirani in 1995. And it looks very similar to ridge regression. It uses an L1 norm on the coefficients and bounds the L1 norm. And the magic of lasso is that it does selection and shrinkage, while ridge only shrinks. And you can see these two cartoons here, which illustrate the phenomenon. You've probably seen this before, but the ellipsoids give you the loss contours of the loss function as a function of beta. Beta hat here is the unrestricted, say, least squares fit. And here's the constraint region. There's an L2 ball that's defined by the constraint on the L2 norm. And basically, we expand the contours of the loss function till we hit the boundary of the ball, and that's the solution. And because the ball is round, you're going to touch anyway in general, and so all the coefficients are non-zero. By contrast, the lasso L1 ball is a diamond, and there's a good chance you're going to touch on a corner, and in higher dimensions on edges, and that implies variable selection. So this next picture shows the lasso solutions as we relax the bound. And you'll see that this, we call this a coefficient path. This traces out the coefficients as we tighten the bound. So if the bound is 0, all the coefficients are 0. As we relax the bound, coefficients grow away from 0. And what you see is the coefficients do that, it's sort of one at a time. Initially, coefficient, what is this? Well, I can't see the number on this one. Initially, this coefficient is the only one non-zero. Then the brown one, which is, we can see that's coefficient 9, is non-zero. So one at a time, they pop out. In this picture, none of them hit 0 again, but they can. Actually, this one goes through 0. So it does hit 0 temporarily. So this is called the lasso coefficient path. And in this case, there's only 10 variables. And so and there was more observations than variables. So at the end of the path, in this case, we get the least squares fit. This was fit in a least squares model. And here we've actually indexed the path by the fraction of the L1 norm. This is the L1 norm of the unrestricted least squares fit, and this is the L1 norm of the current solution. And so this is one way of indexing the path. It gives you a fraction between 0 and 1. Okay? Here we've actually expressed the problem in what we call the Lagrange form. So you can either have it in bound form or Lagrange form, and there's an equivalence between them. So here, as lambda becomes big, that'll push the L1 norm of the coefficient towards 0. Okay? So this profile was actually fit using the Lars package in R, which was developed by the idea by Brad Efron and the package by me and others with Johnson and Tipshrani, who were co-authors of the paper. And this was somewhat of a breakthrough by Efron, where he realized that the coefficient profiles were piecewise linear. And so that meant you could very efficiently compute the entire lasso path with essentially the cost of a single least squares fit. And since when you fit these models, you don't know a priori which value of lambda you want, you essentially need to be able to fit the whole profile so that you can use a technique like cross-validation or AIC or something to pick the lambda. So you need to be able to efficiently compute the whole path. Okay? So paths became the rage. Oh, before I get onto that, this contrasts the lasso path with the ridge path. And the ridge path, here we've indexed the ridge path by degrees of freedoms. That's actually interesting. Well, anyway, you can index these paths by different indexes. This is effective degrees of freedom. Notice the ridge path, everything is non-zero at the same time, and they all stay non-zero as the path evolves, whereas the lasso, selectively variables become non-zero. It's a big distinction. Cross-validation, as I say, is used to, we can use that to select the tuning parameter. And here's the cross-validation. This is tenfold cross-validation in a Poisson example, where we've got the cross-validated deviance. The red curve is the cross-validation error as a function of log lambda, and we've put pointwise standard error bands just estimated from the tenfolds, a crude estimate of standard error, and it helps us select the best value of lambda. Okay, so far, important to have paths, efficient ways of computing paths, so we can do cross-validation to select the tuning parameter. So this led to a flurry of path algorithms following the Lars algorithm. So our groups at Stanford and other groups in other places developed path algorithms for a lot of varieties of lasso problems. There was a group lasso, support vector machines even, elastic net, which you'll hear about, quantile regression, logistic regression. For many other different procedures, we wanted path algorithms. In many of those cases, we couldn't get the path algorithms as efficiently as for squared error loss, because the paths were not piecewise linear. In the cases where they were, we could get some efficiency. Surprisingly, for the support vector machine, that was the case. The cost parameter in the support vector machine has the coefficient profiles have a piecewise linear path. But for a lot of the models we're interested in, the coefficient profiles are not piecewise linear, and that meant the efficiency was not there. And so these problems basically break down when P is very large, the algorithms. So this brings us to the topic of the day, which is GLMNET and coordinate descent. So the idea is we're going to solve the lasso problem by coordinate descent, which means we've got a whole bunch of parameters for a given value of lambda, or the cost parameter. And what we're going to do is optimize each parameter separately, holding all the others fixed. And you'll see the updates are trivial, and and coordinate descent, what you do is you do one at a time, freeze in all the others at their current value, and you cycle around until the coefficients stabilize. Now, this might seem like a really naive algorithm at first, but as you'll become to realize, it's extremely efficient for problems like lasso. We do this on a grid of lambda values, from lambda max down to lambda min, uniform on the log scale using warm starts. You'll see we're able to find lambda max pretty easily. It's the smallest value of lambda at which all the coefficients are still non-zero, and it turns out that's very easy to find for all these kinds of problems. And then lambda zero, when lambda min is close to zero, that means we're close to the unrestricted fit, and so we just make a grid of values on the log scale. And the idea of having a grid is that we'll use warm starts. So at lambda max, all the coefficients will be zero. As we move down to the next lambda, slightly smaller than lambda max, some coefficients become non-zero, but those at the previous lambda give us a good warm start for our coordinate descent. And the finer the grid of lambdas, the more lambdas there are, the better the warm starts are. And as you'll see, you can do this for a variety of loss functions and additive penalties. Now, the amazing thing is that coordinate descent achieves dramatic speedups over all competitors by factors of 10, 100 or more. And we have a 2008 paper, and the GLMNET paper is actually in Journal of Statistical Software. It's listed in the documentation. But there's a long list of other authors who have also worked with coordinate descent, and so we, by far, not the first to do it, and I'm sure we won't be the last. So here's the GLMNET profile for the problem we just saw. So we saw the Lars profile. See, let's go back to it. There it is over there. There's the corresponding GLMNET profile for the same problem. And here you can see our grid of values of lambda. Okay, and there's no approximation at each value of lambda. We get the exact solution. It's just that we don't get the solution everywhere in between. And typically, we just use interpolation for the values in between. If we don't want to do that, you can recompute the solution at any value of lambda and just use the neighboring value as a warm start. So there's no real problem in this approximation. It's just that practically you don't need the values everywhere. So let me tell you about the GLMNET package in R, and I'll explain also why it's so efficient. So it fits the coefficient paths for a variety of different generalized linear models and beyond, and it also uses the elastic net family of penalties, and I'll tell you what those are. Those include the lasso and ridge as two endpoints. So some of the features of GLMNET. The models that we currently can fit are linear least squares models, logistic regression, in other words, binary response, multinomial regression, so multi-response logistic regression, and we have a grouped or not grouped version. And grouped means, as I'll do one of these in the example session. In multinomial regression, you have essentially a linear predictor for each of the classes. And what group does is it selects in the coefficients for a variable for each of those functions, for each of the classes simultaneously, in or out. Or you can have it not grouped. Poisson regression and the Cox model, and also multiple response grouped linear regression. As I mentioned, the elastic net penalty includes the ridge and the lasso and hybrids in between. One of the features is speed. There's a lot of reasons why the GLMNET is really fast. One of the reasons is that the guts of GLMNET is written in Fortran by Jerry Friedman. And I'd say Jerry Friedman's probably one of the top living Fortran programmers in the world. He writes extremely good code. He was one of the inventors of the CART algorithm for regression trees. And he's just a marvel, and I have a huge respect for Jerry's code writing. So our package GLMNET are some fancy wrappers that at the end of the day end up calling this Fortran code. Very, very fast code. We can handle large numbers of variables. And I'm going to tell you about some exact screening rules we can fit that help us fit GLMs on a GWAS scale. In other words, millions of variables. And I'll tell you about that. We have cross-validation functions for all the models. Importantly, we can allow for sparse matrix formats for X. So the X matrix, if it's sparse, that will allow for massive speedups, and you'll see why. Now, typical examples where you have sparse data are document problems. So a document is scored for every word in for the words in a huge dictionary, and most of them are going to be not present, so there's going to be zeros. So in document problems, bag of words, you've got massive amounts of zero, and there's many other applications of that kind. And you'll see coordinate descent is ideally set up to exploit that, that sparsity. We can provide lower and upper bounds for each coefficient. So for example, if you want to fit a positive lasso, you can do it. Some other useful bells and whistles, offsets. Certain GLMs, it's nice to be able to have offsets, so you can have a part of the linear predictor that is given and not fit. So this is often used in Poisson models, where you use an offset to specify the sampling frame. Penalty strengths. You can alter the relative strength of a penalty on different variables. So zero penalty means a variable is always in the model, unpenalized. And that's often useful if you've got some, say, demographic variables that you want to adjust and you don't want any shrinkage on them, but you want shrinkage on, say, a large collection of other variables. You can have observation weights on each observation. You can turn off the intercept. And that's a recent innovation, surprisingly. And we've also added a GLMNET.options where session-wise parameters can be set with this GLMNET.options. And these allow you to set parameters that previously were buried in the Fortran code. And now we give you access to these, and these will control certain aspects of the problem. Let me tell you a little bit about coordinate descent before we go into the examples. So here we got the least squares problem again. And the idea is you're going to fix the coefficients of all of the x's except one. Okay? So that means you can move the other fitted values, well, the other coefficients times their variables, into what we call a partial residual. So we subtract them from y, and then it just becomes a univariate regression problem. And for the purpose of this demonstration, I'm going to assume all the variables are standardized to have mean 0 and variance 1. It's not essential, but it just makes this explanation easier. So then, coordinate descent for this problem amounts to, whoops, I hit a bad key, amounts to two steps. Compute the simple least squares regression coefficient of this partial residual on x. And because of the standardization, this is the least squares coefficient. You can see it's just an inner product. And then soft threshold that, that coefficient, which means if it's positive, you subtract lambda, but if it gets below 0, you set it to 0. And if it's negative, you add lambda. So two trivial operations, an inner product, which is order n computations, and soft thresholding. Now, just note now, if this x is very sparse, so most of the values are non-zero, when you compute this inner product, you're going to use sparse inner product methods, which will just visit the non-zero values of x. And so you can see immediately that's where you get the big savings from sparsity. Elastic net penalty is a hybrid between squared error loss and lasso. And it's controlled by parameter alpha. This is good if you've got variables that are very correlated. Lasso doesn't do that well when variables are very correlated. It becomes a little bit indifferent as to which variable to put in the model and maybe mix in variables. Whereas Ridge handles correlated variables better, tends to shrink their coefficients towards each other. And so this hybrid actually gives you a bit of lasso and a bit of Ridge. And it turns out the algorithm's just as simple. The soft thresholding becomes now soft thresholding by lambda times alpha, because we've got lambda there times, it will be this alpha here. But it's also a uniform scaling by, in a Ridge fashion, by lambda times 1 minus alpha. And so this is the operator there. So it's just as simple. That's elastic net. Oops. Oh dear. So this guy's upside down. Well, I could try and turn it upside the right way up, but I won't. You can just look at it upside down. I'm not sure why that happened. This is an example, and this shows the lasso profile. So try and imagine this upside down. This is a lasso profile. There's the elastic net profile, and there's a ridge profile. And this is for part of a path. This is using some leukemia data. And the thing to notice is that the lasso profile has less non-zero coefficients, and they shrunk less as well. Elastic net has more non-zero coefficients, but they shrunk more. Ridge has all non-zero coefficients, and they shrunk heavily. So I apologize for the upside down slide. So two other important things to tell you about. The one is exact variable screening. When you fit a ridge, say, on a GWAS, the very first variable to enter the model, and this also defines that lambda max, is the variable. So we take y, it's a binary variable, you say, and y bar is the mean, and we take that residual from the overall mean, and we compute the inner product with each of the x's and take the absolute value. The variable with the largest inner product is the first to enter the model, and it also gives, that value is the lambda max. So any lambda bigger than that, everything will be 0. So, and then we start decreasing lambda. Well, you might have a million variables, but what you can do is you can compute these quantities and screen off those with the largest, say the largest 1,000 of those with the largest 1,000, the first 1,000 with the biggest values of this quantity. You can fit your GLMNET path just to those 1,000 variables. And with GWAS, we typically are going to stop when you've got 20 or 30 variables in the model. And then you can go back and check for all the million, including all those that you left out, whether they would have stood a chance of coming into the model. And if they didn't, you're done. So this is an example of screening. Okay. So this is very helpful, and it's led to even better versions of screening. And there's some interesting papers. There's one by Al-Gawi et al. In 2010, and then Tibshirani et al. In 2012, that improve on this. And you can basically screen all the way down the path. And so the idea is very similar. At any point, you've got a current lasso solution, say at lambda L, and you're thinking of going down to lambda L plus 1, some value lower. You now compute the inner product between x and the current residual. Right? This is the current residual. Take the absolute values. And all those that are big, now lambda L plus 1 is bigger than lambda L. So it seems all those that are bigger than lambda L plus 1 are going to be certainly candidates for the model. Because at lambda L, the solution at lambda L, as all these inner products for the active set are equal to lambda L. As lambda L plus 1 smaller than lambda L, we expect a few more to get into the fold. But we go even further. So we take all those that are bigger than lambda L minus the gap between lambda L and minus lambda L plus 1. We call those the strong rules. That's usually a small subset of variables. And then we restrict the GLMNET algorithm just to that subset of variables. We compute the solution, and then at the end of that, we check for all the variables, the whole lot, and make sure that we have the solution for the whole lot. And that checking is trivial. It's just inner products. And that gives you a dramatic save-up. So here's an example where there were 5,000 variables. And the dotted line here, the dashed line, are the variables that entered the size of the active set as the model proceeded. And the green dots are showing the size of the strong set that we got by screening. You can see it's, in this case, it's always slightly a little bit more than those that we actually need, but much less than the full set. So that causes a dramatic speed up in the convergence of the GLMNET algorithm. Okay, I'm going to skip to the examples now. And the first example I'm going to show you is an HIV drug resistance problem. There's just over 1,000 observations and 217 variables. They're mutation variables, and we're looking at the response to protease. Well, you can read it here. I'm having trouble reading on the screen here. Okay, so I'll skip out of this and bring up this. And let's see, I want full screen view.
You can click on the upper right-hand corner of RStudio as well.
Oh, there we go. Okay, thank you, Ray.
Yep.
Okay.
Yeah, that looks good.
Good. Yeah. So, as you can see, I'm using, well, if you don't know RStudio, I'm using RStudio here. It's, in my mind, I've just started using it, so I'm a bit of a novice, but it's very good for making presentations like this, and I think it's probably good for lots of other things too. So normally I do my own R work in Emacs. I'm an old Emacs hacker, but for presentations like this, I think RStudio is wonderful. So we've got a script up in this panel over here. There's the R workspace and session window, and you'll see plots will appear on the right here. So we're going to library GLMNET. See, so I just do control-click up here, and the commands get sent below. The first thing I'll do is do a help on GLMNET. Surprisingly, people tend not to use the help files as much as they should. And in this case, I do encourage it, because there's a lot of different options in GLMNET. And although the help file probably could be better than it is, it does give you a description of all the options. And so here we see the choice of the models that you can use. So that's an option. Observation weights, offset, various parameters that you can set. The recent ones are lower limits and upper limits on the coefficients, and other options. Also, important ones are standardized. You can have by default, the variables are all standardized, which incidentally generally makes sense for lasso models, because the penalty treats all the coefficients as equals. And so if the variables are in different units, it really makes the interpretation of the penalty a little troublesome. And lambda, usually you let GLMNET pick its own sequence of lambdas, but you can actually supply your own sequence. Okay, so help files are useful. All right, so let's load the HIV data. And we look at the dimensions. There's 704 observations, 208 variables. And we fit GLMNET, the coefficient path, boom, very fast, and plot the fit. And there's the coefficient profile. By default, that's plotted against the L1 norm of the coefficient vector. And so since as we go from left to right, we relax in the penalty, the L1 norm of the coefficient vector is monotone increasing. Okay. If we just type fit, we can get a printout of the fit, and it's run off the screen here. But what you can see is there were 100 values of, well, it used 97 here. I'll tell you why. And what it gives you is, as we decrease lambda, you see as the values of lambdas decrease, this is lambda max. It tells you degrees of freedom, which is the number of active variables, number of variables with non-zero coefficient, which for a lasso is an estimate of the degrees of freedom. And it gives you the percentage deviance explained from over the null deviance. So this is like a generalization of the R squared, okay? And we actually asked for 90, we asked for 100 lambdas. It stopped it at 97 of them. And the reason being is that this percentage deviance explained stopped progressing. So basically the model was changing very slowly. And that's one of these default parameters that you can change in glimnet.control. So in the call here, we just gave it the X and the Y, and it did the fit, okay? And likewise, we can run cv.glimnet to do cross-validation, and it by default does 10-fold cross-validation, and we can plot the cross-validation curve, and here it is. And You can see the standard errors are fairly narrow. And the two vertical lines, one is at the minimum, and one is the one always on the more conservative side is the lowest point within one standard deviation of the minimum. It's a way of sort of getting a good pragmatic value of lambda it's close to the minimum, but it's going to generally give you a sparser model. And at the top of these plots, we see the number of active variables. So over here, there's under 30, maybe 20 non-zero variables. Around here, there's 51. Okay. All right. So next, we're going to make a prediction. So we call the predict method for GLMNETs. We give it a test vector X, a matrix X, to make predictions at. Okay. And then these are commands just to compute the test error. So this predict function is actually going to make predictions at every value of lambda. So it's going to give you a matrix of predictions. And then I compute the test error in this simple command here for each of those predictions for each value of lambda using computing the squared error mean squared test error. And then I'll add those to the plot. And there we see it. And cross-validation pretty much did the right job here. We see the test error also happens to bottom out. In fact, it seems to bottom out at the more conservative value of lambda here. And we can put a legend in the plot. So very quickly, we were able to get the cross-validation curve and the test error curve. There's some options in the plot command for GLMNET. So by default, it plots against the L1 norm of the coefficient vector. You can also plot against lambda itself. And of course, then you get a different plot. So as lambda gets smaller, more coefficients enter into the model. In fact, here we're plotting against the log of lambda. And you see the coefficients growing. And finally, this is an interesting plot. We plot against, it says devia, and what that means is we're plotting against the percentage deviance explained. And this was a case where the model towards the end of the path got to overfit. And when that's the case, often these plots are dominated by, like when you plot against the L1 norm. Let's just go back to this plot again. Sorry, this plot. This is plotted against the L1 norm of the coefficient vector. Well, right at the end of the path, the coefficient vector tends to, and here we're sort of right at the end of the path, or almost, in that the coefficients aren't changing much, and they've all got very big. The L1 norm's really large, and when we go down to this plot again, we can see when the coefficients are really large, we're pretty much overfitting the data. The percentage deviance explained is almost 1, or the fraction of deviance explained is almost 1, which is an overfit situation. So it gives you a perspective, a different perspective of the coefficients. Okay, here's the internet data, internet ad data. It's a big data set, so let's see, I'll attach it. Let's look at the dimension. It's got 2,300 rows and 1,400 columns, so that's pretty big. I do class of X, and we see that it's in sparse matrix format. You can see it's a form DGC matrix, so it's in column sparse format. And if we ask for the number of non-zeros, there's only 3,900 non-zeros, whereas there's over potentially 3 to 4 million entries in the matrix, but only 39,000 of them are non-zero. So this is a sparse matrix. In fact, it's got 1% non-zero entries. Okay. The response is binary in this case, mostly zeros, some ones, and we fit a GLMNET model. Now we call GLMNET with family equals binomial to tell it it's a logistic regression model. And we've got standardize equals false, so we don't want to standardize the variables. We plot the fit, and there's the coefficient profile. Relatively small number of non-zero coefficients. Okay. Here we're going to recompute the fit, but we're going to put upper and lower bounds on the coefficients. I'm doing this in a sneaky way. I'm using the R update function. I bet not too many of you know about the update function. But any model that has a component of the fit object, in this case, GLMNET does this, which is called a call, which gives you, let's go down here and see what fit $call looks like. Fit $call. See, it's an expression that was used to create the fit. For any model that has such an object, you can use update. And it'll use all the parameters that were used in the fit, plus any other ones that you give it. So in this case, we're going to give lower and upper bounds on the coefficients. And now we plot, and sure enough, this new fit has got the imposed bounds on the coefficients. So this can be useful. Often 0 is a good lower bound. You want to have a positive lasso, and we can also plot against the deviance here. Now, a fraction of deviance explained. So again, this is quite a big problem. 2,000 observations and 1,400 variables. We can run cross-validation, 10-fold cross-validation, pretty fast. We can plot the fit there. It looks kind of staggered. It's a strange cross-validation fit. I'm going to redo the fit using, without the standardize option. We plot the fit. Oh, we see we got many more non-zero coefficients. So in this case, standardization made a big difference. And we'll run cross-validation here. And we'll use cross-validation as various arguments. And one of them is you can say what type of measure you'd like to cross-validate. In this case, we're going to use area under the curve, which is popular for classification problems. It's somewhat technical. It's the ROC curve for the classification. And then you compute the area under the curve, which is a measure of classification performance. And close to 1 is good, and so here cross-validation is using that as a basis for cross-validation. I encourage you to look at the help file for cv.glimnet. It gives you some of the various options. The final example is a multi-class classification problem. This is what we call the Tomeo data. The variables are gene expression variables. We've got 13 different response classes, and each of them are rather sparsely populated. These are different cancer classes, and the variable is this matrix X3. There's 16,000 genes. So the training set has got 144 observations distributed amongst these classes. There's 16,000 genes, so that's a lot of variables. And we'll fit a GLMNET model to that. And that's going to take a little bit longer than before because of the number of variables, but not that bad. And now when we do a plot, we actually have to make a layout because there's going to be a plot for each coefficient for each class. And there's the plot of the coefficients for each of the 13 classes. Okay? And we can do cross-validation for that. And yeah, I choose n folds equals 8 because you'll see 8 is somewhat a special number for these. Many of the classes had 8 observations. And so it kind of makes sense to use 8-fold cross-validation. So there's a hope of getting 1 observation in the class. In fact, you could ensure that when you do it. Now, this is the case where we didn't insist that that the same variable was non-zero for each of the classes. So it's a little hard to see here, but for each of the classes, different variables can be non-zero. Whereas we have another version of the multinomial, or the group multinomial, where you can insist that the coefficients are non-zero together for each of the classes. So you can see I'm trying to talk my way through the cross-validation here. This is running on my MacBook Pro, Now, it was faster yesterday. I'm not sure why it's taken a little bit longer today. Um, but we have to just basically wait for it. This is probably something I should have pre-computed.
We're good with time, so don't worry about that.
Yeah, yeah, it was definitely faster yesterday. Yeah. Okay,
There we go.
it came back. Thank you. There's the plot. It seems in this case, the smallest value of lambda gives you, the minimum. This is the multinomial deviance, cross-validated multinomial deviance. And the one standard error rule takes us over here. You can compute the prediction error. And in this case, it's 35% errors. You can actually do better if you use the elastic net model in this case. You can also use the grouped multinomial. I'm actually not going to do that here because, well, I can. I mean, it takes a little, the grouped option takes a little bit longer than the ungrouped option, but we're not actually doing cross-validation here. We just run in it once. And so we'll let it run. And actually, that's close to the last thing we do. So, and then we'll look at the coefficients when it's fit. And there, the coefficients. Now you can't. It's hard to actually see that the coefficients are grouped, but believe me, they are. Okay, so that's the end of the demo, and that's the end of my presentation. And so now we're gonna open up for a question and answer session. So I guess I'll hand it back to Ray.
Well, thank you, Trevor, for that great demo. And if anybody in the audience has a question, you can send them through the questions pane in the GoToWebinar control panel. So you have an orange button on your GoToWebinar control panel that's either pointing to the right or pointing to the left. That allows you to maximize and minimize your control panel in a toggle-like fashion. So once it's maximized, then you can go into the questions pane and send a question. So I'm starting to see some questions right now, and we can just start working through them. So the first question is from Michael, and Michael asks, does GLMNET allow for survival analysis with time-varying predictors?
Good question. The answer is no, I'm afraid. It does do survival models, so that's the Cox option in GLMNET. But at present, we don't have time-dependent variables.
Sure.
Normally, one can do that with a Cox if you have a general Cox model that allows for start and stop times for each observation. But at present, we don't have that in GLMNET. But that's on our list of things to do.
Mm-hmm. Another question from Scott. So in the logistic regression example, would you consider applying observation weights to upweight the relatively rare response class?
You can do that. It doesn't really make any difference. By upweighting the rare response class, what you really change in the model is the intercept, and the coefficients themselves really don't change, much. So it's not necessary.
Okay. Here's a question.
You can do it if you want to. Yeah.
Okay. Here's a question from Ginwa. Is there any advantage to using GLMNET when the number of variables is reasonable and actually less than the data?
Yes, there is. There's various advantages. The code is still very fast. When you do it using squared error loss, it uses a kind of caching, and so works with, it pre-computes or caches the inner products, and so it doesn't have to compute them. You can see that in our paper, and so it's so there's speed ups there, and if the data's, if the X matrix is sparse, you can also get advantages from that. Yeah, so GLMNet's fast either way.
Sure. Okay, here's a question from VJ. Is there going to be a recording made available? Yes. So I can answer that one. So we're currently recording this webinar, and it will be posted within the next 7 days. So everybody in the audience right now will get an automatic email from the Gotowebinar software engine, and it will give you a link to go get these, the video as well as the slides. So stay tuned for those. They should be up within the next 7 days and probably even sooner. Okay, here we got a question from Layla. Can you talk a bit about how to obtain standard error estimates for the non-zero coefficients?
Ah, yep, that's an interesting question, Layla, and I expected a tough question from you. You know, there's a lot of work going on right now on standard errors for lasso and elastic net coefficients. Apparently, there's a paper by Buhlmann and co-authors that's just come out. There's also recent work by Tibshirani and co-authors on doing tests for coefficients. But if nothing else, you can use a bootstrap, right? So suppose you run GLMNET and you use cross-validation to pick lambda, you select your lambda, and now you've got your coefficient profile. Well, you can bootstrap that whole process. So since GLMNet's really fast and the cross-validation's fast, you can run GLMNet for 100 bootstrap times, and so then you can look at you can get the sampling distribution for the GLMNet solution, and you can get that information from there.
Sure. Here we have a question from Ling Kang, and just asks if it's possible to get the code you used in the demo. Could that be posted with the slides and the video?
I will post the code on the website in the same place as these
Great.
slides in the demo. Yeah.
Okay. Here's one from Ilya. Can GLMNet be used to fit IRT models?
Now I'm blanking on what is an IRT model.
So Ilya, if you can send that in through the question pane as to what an IRT model is. Oh, okay. It's item response theory. Are you familiar with item response theory models,
Yes,
Trevor?
I am. Yeah, a little bit familiar with it. GLMNet hasn't got any specialized features for IRT models. I haven't really worked with them much myself. But given that GLMNet can have some subset of variables penalized and some not penalized, it's possible that it could be used for that, but I'm not sure.
Okay.
It may be possible.
Here's a question from Steve. Is the type.multinomial equal grouped argument penalizing differences of the same coefficient between the different models?
No. What it's doing is, instead of having a separate, suppose you've got variable x3, and you've got 5 classes. So there's going to be 5 coefficients for x3, one for each class. Ungrouped means you just have a separate L1 penalty on each of those coefficients. Grouped means you have an L2 penalty on that coefficient vector, all 5 coefficients. And it's not L2 squared, it's L2. It's called a grouped lasso penalty. And what that does is it selects the whole group in or out. And if the whole group's in, all the coefficients are non-zero, but still shrunk towards 0.
Okay. So here we got a question from Gregor. I have tried the graphical lasso and it seems very RAM consuming. Is this simply due to the n by n size of a matrix, or could the code be improved further on?
The answer is probably both. Usually it's just the n by n size of the matrix. We try and avoid making copies of the matrix, and the Fortran code certainly doesn't make copies. So, it's really limited by problem size. Now, if you have a very big problem, and especially with a very large number of variables, so I'm thinking like GWAS scale, and you find you can't get all the variables in memory, you can sort of manually implement these strong rules. So screen out the variables that have small inner products with Y, run your GLMNet on the subset of the variables, and then later go back and check to see that none of those other variables should have come into the model anywhere in the path. So that's a kind of swindle that you can do, still get the solution that you're interested in, but without actually trying to put all the data in memory.
Okay. Here's one from Ian. when fitting the cancer genomics data, it was said that there were 8 cancer classes, but table Y showed 16. Could you explain this?
Now the table was 16, but there were actually 13 classes, not 8.
Oh, okay.
The smallest number of observations per class was 8. That's what that was. So there were 13
Observations per
classes.
class. Okay.
Yeah, and so I could only draw it in
Sure.
a.
Okay, here's one from Ling Kang. What is the largest size of P and N that you can take for GLMNet? I Can it handle GWAS data, or do I need to do pre-screening?
Well, you may need to do pre-screening, but there's no limit on P or N. The limit is to do with how much memory you've got on your machine, so that will determine the limit. So if you happen to have a big brute of a machine, with a gigabyte, with many, gigabytes of RAM, you can do much better. So my machine's got 8 gigabytes of RAM, but there's some machines that have 500 or more, and
Sure.
so it just depends.
Okay, so we got 3 more minutes. So here's one from Mike. I am a grad student. I'm fairly new to GLMNet, and we are choosing to either do lasso or group lasso on my data. Do you have any advice?
Well, it depends on your data, Mike, but GLMNet doesn't do group lasso for general problems yet. So if you want to use group lasso, there's other packages in R for doing that. GLMNet does group lasso just for the multinomial problem or for multi-response regression. But I would first of all try lasso and elastic net before going to the more complicated group lasso.
Sure. Okay, here's one from Paul. Concerning random effects regression, if we write out a model as penalize ML, similar to Pine Hero and Bates, we arrive at a very wide sparse formulation similar to yours. Have mixed model folks tried to adapt your algorithm for estimation of those problems?
Yeah, that's a good question. If they have, I'm not aware of it, and we haven't done it yet. But that certainly is a way to go. So a GLMNet model, ElasticNet, and Lasso can be viewed as it can be used as a random effects model with a prior distribution on the coefficients, and so you can build in other random effects as well, and consider hybrid models, but we haven't
Sure.
done that.
Okay, here's one from Dirk. Correlated variables, ElasticNet helps. What is the benefits of hybrid model compared to Ridge?
Well, the problem is Ridge does no selection. So um, the elastic net will take care of groups of correlated variables by shrinking their coefficients together, but it'll also be able to select in or out groups of variables. So it'll still do variable selection, but that takes better care of correlated variables.
Okay. And here is one from Joe. Does GLMNet work with big memory or FF?
If
Yeah, Joe, could you type through the chat window what FF stands for? And then while he's doing that, you could address big memory. He might be referring to things like Hadoop or similar.
Yeah, there's there's going to be there's going to be hybrids of GLMNet that are going to emerge for big memory and for distributed computing and parallel computing.
Sure.
At this point, we don't have anything in place.
Okay. All right, we have some questions left, but we're at the top of the hour. So what we can do is, if your question did not get answered, 2 to 3 hours from now, you're going to get an automatic email from GoToWebinar, and you can go ahead and just send your question to that email, and I'll forward it on to Trevor, so that way everybody can get their questions answered today. And I just wanted to thank everybody for coming, and it was a great webinar by Trevor on GLMNet. Anything you wanted to make any closing remarks, Trevor?
No, it's just this was not as painful experience as I thought it might be, and I hope it was useful to the people who stayed online.
Great. So yeah, in 2 to 3 hours, everybody in the audience will get an automatic email with a link to the slides and the video and the code. And this will all be posted within the next 7 days. So be patient for that, and it will be on the internet. So once again, everybody, thank you for coming, and we're going to go ahead and shut down the webinar. Have a nice day or a nice evening wherever you are in the world, and take care.
Bye bye.